with Sistemas and Interdisciplinar. So welcome. And here he will be working with Pera Colette and myself.
So hello everyone again. So today we have this seminar which is given by Konstantin. All of you know him, and he's doing his PhD thesis work with Ingo Fischer, and he's going to present this work.
Yeah. Hello again. Thanks for coming. I'm going to present to you some results that were produced together with these nice people, all my collaborators. All of you know Javier, Daniel, Miguel, and Ingo from here. And some of the results were produced, or research was done together with Jordi Tiana-Alcina, Carmen Torrent, and Jordi Garcia-Halbo from UPC. And together with Valentin, who was back then still working in TU Berlin. And Otti Dois, back then she was working in the Universidad de Brussels. Yeah, the title is Dynamics and Synchronization of delay-coupled semiconductor lasers, and that says it all. So we are just gonna jump into it. First, the motivation. Why do we care about delay-coupled systems? I mean, those are very fundamental in a lot of different research areas. All of you know, I guess, because all of you work in different kinds of research areas. Of course, we as the nonlinear photonics group are interested in lasers mostly, but also delay-coupled systems are very interesting and very important in brain dynamics and neuronal systems and social systems, traffic, and so on. And why are lasers especially so interesting? Because they are in general good test beds for delay-coupled nonlinear systems. We can test certain hypotheses with laser systems, and they allow for richness of different dynamical behavior, including chaotic intensity dynamics. And also, this laser systems can be used for certain applications, for example, for chaotic communications, for key exchange over a public channel, and also, for example, from Neil's work, random number generation. So, first let me note where the chaos and semiconductor lasers come from. Normally, if you have a solitary laser, semiconductor laser, coupled to nothing, you just measure the intensity output. We have something called the continuous wave output, so more or less stable intensity profile. This is of course a symbolic picture because on top of that you have a certain amount of noise. But now if you couple two or more lasers, which is then of course a time delayed coupling because the light needs some time to reach the other laser, or you couple some feedback of the laser to itself that induces chaotic instabilities in the intensity output, and then you get time traces like this. And these chaotic laser output can be synchronized, which is most of the talk is mostly about, and then also used for applications. This is now a short outline of my talk. First, we had the motivation already. I'm going to talk a bit about stability of identical synchronization and sometimes zero-lag synchronization of these chaotic laser outputs. Then do a part about transverse instability and the phenomenon called bubbling. Then I'm going to show to you some experimental results we produced in the lab, and also to confirm certain hypothesis. And also at the end I'm going to give you an example for an application. Right. So first we look at this kind of setup. We have two lasers coupled face to face with a coupling strength K and having appropriate or some kind of delay time tau. It was shown that the identical synchronization, or in this case the zero-lag synchronization of the outputs, is an unstable solution. Instead, what we get is not zero-lag or identical synchronization, but synchronization of the leader-lagger kind. So that means that the leader basically induces the dynamics in the laggard, and this then in turn synchronized with the leader. But in this kind of configuration with symmetric roles, basically we have switching roles of the leader and the laser in this kind of system. And the delay time in this delay lag in this kind of synchronization scheme is then corresponding to the delay time tau. Now, if we put a so-called relay, or for example in the laser setup, a semi-transparent mirror in between the two lasers, it was shown that the scheme allows for identical or even zero lag synchronization. So we have here the mirror in that case. The blue lines are depicting the coupled signals. So K is the coupling strength, L is the feedback strength, because in turn each laser output gets reflected here at the semi-transparent mirror and put back into the laser, and then it turns again induces chaotic dynamics. And this really, in that case, or in that manner, really allows for zero lag or at least identical synchronization. And if these different delay times tau 1 and tau 2 are equal, then we even have zero lag synchronization. Otherwise, we have a time shift corresponding to the corresponding difference between these two delay times. So, we're going to start with the influence of certain mismatches and symmetries in the system and how these influence the synchronization solution, the stability of these solutions, and the dynamics therein. So let us first assume that the delay times are equal. So we have a symmetric setup regarding the delay times, and then we can constitute these generic equations first. So we have the state variables x, 1 and 2 here, and this function f accounts for the dynamics of these systems. Here we have again the feedback strength of system 1 to system 1 with the delay time tau, and here is the coupled signal from the other system with the coupling strength k, and again the time delay tau, and vice versa for the other one. And what we now want to investigate is the stability of the identical synchronized solution. That would basically mean x1 of t equals x2 of t. And especially now in the relation of the coupling strength k and feedback strength L, especially regarding certain symmetries. So for that we introduce two new variables. First the symmetric variable s, which is basically the mean of the two state variables at the time t, which then basically produce or describe the dynamics inside the synchronization manifold. This wobbly thing here is supposed to be the synchronization manifold. These lines here is the dynamics inside the manifold, and now the other variable is a of t. This is antisymmetric, and those describe the dynamics transverse to the synchronization manifold. So everything that goes outside of the manifold here, direction a, perpendicular. And this is basically the difference of these two state variables. Then we can look at the time evolution of these two variables, s dot and a dot. And two things are obvious now. That the dynamics in the synchronized state, so s again, depends on the sum of the coupling and the feedback strength, but not on the difference. So if we have a mismatch of coupling and feedback strength, so a non-symmetry, it doesn't influence the dynamics in the synchronized state. That is important, in the synchronized state. But the dynamics transverse, in the transverse direction, is influenced by the asymmetry again. So here. So if we have a mismatch, then this influences the asymmetric variable, so the non-synchronized state. The stability of the zero lag solution can now be investigated by introducing a transverse perturbation, so this delta A, and this is then the time evolution. Here we have the df is the Jacobian of the dynamical function f, and here again we see the influence of the mismatch between coupling and feedback strength. And we see if we have a totally symmetric setup, so equal feedback and coupling strength, this term vanishes. and then we can simply calculate the stability with the instantaneous eigenvalues of the Jacobian df again along the trajectory s of t, so the synchronized state. Now let's apply this to the laser model. This is again.
Konstantin.
Yeah.
But you talk about the synchronized state, you talk about variable s.
Yeah.
S is the sum.
Yes.
Why s is more important than the difference for the synchronization?
I mean, the difference is describes the non-synchronized state, is obvious, right?
Right.
And the sum is then basically just the perpendicular solution, if you will. So
I mean, the claim that since in the equation for S only L plus K appears, that this is the combination which is relevant for synchronization, I don't understand the claim mathematically.
okay, I mean, if you assume the two lasers to be synchronized, then the sum of the mean of the two state vectors basically is just as it is, right? Because they are synchronized anyway. And what we want to produce is two perpendicular variables, if you will. So the unsynchronized, the antisymmetric variable going outside of the synchronization manifold, and then the variable inside the synchronization manifold. And that's the easiest way to produce these kind of variables. Okay. Yeah. So here we have the generic equations again, and now for the laser model we have been looking at mostly is a rate equation model. So the function f of the state variables E, this is the electric fields of the lasers, and n is the carrier number. Equals then this here now. There are certain parameters, so this is called alpha factor. This is the Langevin noise term here in the field equation. We have here the pump current of the system. This is the timescale factor. Yeah, and that's basically it. If we now, this is a numerical result versus we have the correlation, the cross correlation of the two lasers output versus L and K, so the feedback strength and the coupling strength, and we can see that it has a certain LK symmetry, right? So along the separatrix we have a symmetry, so the zero lag state only depends on the absolute of this difference.
Yes. Well, I expected you to. I was confused because all your argument is with a single equation per laser, and then you see that the rate equation has at least two complex equations or in fact three. Laser is a three-dimensional system.
Depends on what it is.
Well, yeah,
absolutely. But this x basically is a state vector, so it's not only one variable, but a certain.
Well, I don't see very clearly how. I think that some of the arguments on which combination of parameters depends in each variable, I think this depends on the number of dimensions. But anyway, this is probably not very important. What the thing is that cross correlation is the cross correlation between intensity, cross correlation between fields.
Between intensities.
First, continuing with his argument. I cannot see the same. L is a constant or something?
Sorry.
L and K, a constant or matrices?
If you look at a certain situation, then yes.
They're constants.
Yeah.
I don't see how
anyway.
the same coupling between the electric field can be the coupling with the carriers. I don't see how it would be the same constant in both cases.
Actually, that is true. I cropped the model a bit. Actually, the coupling only takes place in the field equation, which is true. That's okay, that's a certain...
And your previous argument is kind of sloppy.
Sloppy, okay. Yeah, okay, I can't...
No rigorous.
Manifold sounds good, but the argument...
Okay.
Excuse me, I mean, I don't understand your sentence. With L is equal to K, and for example, you have 0.2 and 0.1, they have obviously different values, right? So I don't understand the sentence.
What do you mean?
So you say zero synchronization depends only on the difference, the absolute value of the difference, right?
Yeah.
Imagine that you say that this is zero. That means the diagonal. In the diagonal, the difference is zero.
Yes.
And the colors mean different values.
Yes.
So it depends on something else.
Yes, that is true. But if you reach a certain threshold coupling strength, this would be my next slide. Then from that on, you can achieve zero-lag synchronization. Of course, you need a certain coupling strength for the two systems to be coupled, and from which on you reach synchronization. This is depicted here by these lower correlation values. But in general, you need the equality between these two parameters. But for example, if you choose smaller values, then you don't get a synchronized solution anyway.
But even if what you mean is the difference between the blue and the green, it's not true that depends on the difference. And even in the equation, I don't agree with your sentence, because it's true that for the A, when the difference by the center is there, but as the two equations have coupled, I mean, the influence of the difference is also appears through the edge and the coupling, right? So it's not that, I don't know if you understand what I mean. I mean, when you have the equations, it's true that when L and K is 0, for example, give the same, and the second equation is the same, but the first one is not. And the second one is entering into the equation of the A value. Then I don't see why you say that the only thing that matters is the difference between L and K. Because you don't decouple the two equations. So you don't decouple the two equations.
Okay.
That means that it is entering
Okay. So I formulated it a bit unclear maybe. Of course, the absolute values of the coupling and the feedback strength via the dynamics influence the unsynchronized solution as well. But the idea was that the main feature is that the difference, the mismatch between the coupling and the feedback strengths induces certain desynchronization or instability of the synchronized solution. That was the main point. Of course, the parameters as they are influence the dynamics, and by that also influence the synchronized.
Well, yeah, okay. Well, I was reading the sentence there, and then I think the statement.
There's no only.
Maybe at the first order.
That's true. I mean, I didn't write only here, but you're right. It was a bit unclear. Sorry for that.
I think it's also that L and K are not independent. I mean, the sum is 1 in the ideal system, so you cannot just choose randomly on.
So L and K, they
Yes.
Why?
You cannot have more reflection and transmission than one.
Since we are looking at this relay component as in this case as a semi-transparent mirror, and then of course you have transmission and reflection, equal or lower to 0, and the sum must be 0, of course. Right, but let's move on. So, now, what we have here is a plot against this very important parameter, the coupling strength K, and what we see here is the blue line is this so-called parallel Lyapunov exponent, so it describes basically the chaoticity of the dynamics inside or outside the synchronization manifold, doesn't matter. So, you can see here that increasing the coupling strength first increases the chaoticity and then it goes down a bit. But the more important value here is the lambda perpendicular, and this is the so-called largest transverse Lyapunov exponent. And we know that if this is smaller than 0, then the synchronization manifold is stable, transversely stable. And important bifurcations here are B1 and B2, so-called blowout bifurcations. And if we, as we can see, if we have a coupling strength bigger than B2, then we have transverse stability, and here smaller than B1, this small part here, we have also transverse stability. Otherwise, which we should not confuse it with, is the global transverse stability, which would between those two blowout bifurcations. And that's just the reason why in this correlation plot here, below a certain coupling strength and feedback strength, we don't have this kind of synchronization or correlation that is corresponding to that. So, what does bubbling then actually do? I mean, we know that, or like I said, I didn't say that actually, sorry. The bubbling phenomenon is induced by a transverse instability of invariant sets. So invariant sets in the otherwise transversely stable synchronization manifold. This would be a number of periodic orbits or whatever. And this transverse instability, this subset, induces intermittent desynchronization events. So we can see here experimental results. Actually, these are intensity fluctuations of laser outputs, and this is the intensity difference, so basically the synchronization error. And we see here these spikes, these peaks here, and these are desynchronization events, or intervals of unsynchronized behavior, and these are attributed to the bubbling phenomenon. And the bubbling phenomenon is usually induced by noise or by parameter mismatch, just like the mismatch between coupling and feedback strength, but I will go into that later. But it's obvious that if you have the occurrence of these desynchronization events, that this will overall decrease your synchronization quality, right? So, yeah, here again a bit more clear, the rate equation for a single laser with feedback. So here we have the coupling strength only in the field equation and not in the carrier equations. But since the carrier equation are coupled to the field equation, these are then, of course, influence themselves. So, and the chaotic dynamics of these delay coupled lasers are organized, governed by the so-called external cavity modes. These are basically periodic orbit solutions, induced or produced by certain geometric interference effects and so on. And these are of the form of this shape. So we have a constant amplitude here, a constant frequency, omega, and a constant carrier number, n. These solutions are usually, they lie on a shape of an ellipse. And also, if we assume synchronization between two lasers, we can then model two synchronized lasers as one. As one laser with two different feedbacks, namely, then correspondingly feedback 1, the normal feedback that we had before, and feedback 2 would then correspond to the coupling, to the other laser that we had before. And the transverse stability of these modes can then also be calculated with linear stability analysis. Okay, so this is what we have here. This is the ellipse shape I told you about just now. And these dots, these circles here and these triangles are the modes. The blue ones are transversely stable modes, and the red ones are transversely unstable anti-modes. These lines here depict the chaotic dynamics of a single laser with feedback. So we can see here that the trajectory basically in this phase space, the carriers here and the frequency here, this is basically calculated with the Tor averaged phase difference. The dynamics itinerate down here, this ellipse, and in turn we can see a power buildup, and then at a certain point in time we have a so-called power dropout, namely when the trajectory or the dynamics hit one of the unstable anti-modes. This happens in a single system. That just means that we have a change in dynamics, and then the whole thing starts over again. And in the coupled system, in the coupled system in synchronized state, this basically looks the same. But then these are the transversely unstable antimodes, and this collision here with an antimode, of the dynamics with an antimode, would then result in a desynchronization. This is corresponding to a dynamical regime called low frequency fluctuations, this called like this because we have these dropout events here. this. This basically constitutes an overarching slower time scale, some kind of slow frequency fluctuations, as the name suggests. If we now increase the pump current, we have in general larger intensity fluctuations, kind of obvious, and that results in the fact that we have more collisions with these kind of anti-modes than in this regime. And this is then called coherence collapse regime, but I will get into that later. Going back to the coupling mismatch. This is basically more or less a similar thing that I showed you just now. So here we have the dynamics in the synchronized state. So these lines basically describe the synchronization, the dynamics of both lasers. This is basically corresponding to the S variable, and this light line here is the dynamics in the unsynchronized state. So here we can see collision with an transversely unstable antimode. We have this power dropout here, the lasers desynchronize, the trajectory gets ejected back here, and then here the lasers resynchronized, and the same thing goes over again. This is again this is now field absolute difference, so almost the same as the intensity difference, and here we can see the desynchronization, right? Because here we have the spiking of the intensity difference. If we now increase the difference, the mismatch between the coupling and the feedback strength, but keep the sum constant, and as we saw before, this should not change the dynamics in the synchronized state, but change the stability of the synchronized state. So, and we can see here now that more modes are transversely unstable, so the dynamics in the synchronized state look more or less qualitatively the same, but it just takes the two lasers longer to resynchronize. So this event here, this desynchronization event, is just longer, but the dynamics are qualitatively the same. These are numerical results, just to mention that. So, now we look at a different kind of mismatch, namely the delay mismatch. So this would be the case if tau1 and tau2 are not equal. So we can constitute this variable delta tau, this is basically just the difference. And now we have not a zero-lag synchronized solution, but identical synchronization with a time shift corresponding to the delay mismatch, so the difference of the delay times. The S and A variable then look like this, basically more or less the same, just introducing this mismatch here. And again, the evolution of the small transverse perturbation, assuming the equality of coupling and feedback strength, looks the same as in the case without delay mismatch. So we can say that the delay mismatch itself does not influence the synchronization or synchronization quality. But if we combine now both kind of the mismatches, we can see, again, this is the same kind of plot. Here we have a mismatch, the delay mismatch, and then here we have the scan via L and K, and we can see, comparing with the case without delay mismatch, that now the system is more sensitive to a delay mismatch if we also have a kind of coupling mismatch, right? Because this the region here of higher synchronization or higher correlation is narrower around the separatrix than here in the case without delay mismatch. And also the dynamics depend on the delay mismatch, because as I told you earlier that symmetric delay times would result in the ECM solutions lying on an ellipse shape, right? But if we now have a certain delay mismatch, this shape gets distorted and we get these kind of patterns, so intertwining, wobbly, ellipsy shapes. And this, of course, also changes the overall dynamics of the laser, synchronized or not. And some specifics. Like you can see here, we have the normal itineracy down the ellipse like earlier. Here we have a rational ratio between the two delay times. Nothing special, more or less, to see. But if we have if we have a delay times ratio just a bit bigger than the rational ratios, then we can stabilize the dynamics. Here, this small blue part is actually stabilized dynamics on one of the ECM modes. That's why there's the arrow. Arrow, not arrow. And what we can also see is that similar modes, that's similar, so like in the same region of the phase space, have similar transverse stability properties. So again, these here, the red ones are the transverse unstable anti-modes, and the green ones are the transversely stable modes. This is now to illustrate this a bit further. Here we have a bifurcation diagram of the intensities versus the delay mismatch with an overall delay time of 1000. And here are certain zooms. So we can see here for small delay mismatches, for very, very large ones, or for delay time ratios of, for example, here, 333, that would correspond to 2 to 1 ratio of the two delay times. Here, around those, we get this narrowing of the intensity distribution, which then would mean stabilization of the dynamics, for example, 2 ones in the mode. Let's go to the experimental results that we produced. First, we looked at this kind of setup. This is a fiber-based fiber optics setup. So two semiconductor lasers are coupled with fibers along this red path. OC means optical coupler, so here these are the percentages of the intensities that are coupled actually in the one or the other direction. And the most important part is this here. This is so-called fiber loop mirrors. This takes over the function of the semi-transparent mirror, basically because both light signals go into this loop. This is an optical isolator, they only go one direction. And because of these 50 couplers here, we have a symmetric kind of operation. So this would mean we have more or less symmetric coupling and feedback strength, because each signal, whether it comes from this laser or from this laser, gets coupled back in each direction. So coupling and feedback signal. This is an exemplary time series of the intensities again. We see here very, very nice synchronization. Actually, we had correlation coefficients of up to 0.95 over a time interval of 20 microseconds. That is very long in laser times. And what we can see here especially is this is a desynchronization event. Here you see the red one and the black curve are not lying above each other anymore. And this is the synchronization error. So this would be viewed as a desynchronized event or a bubbling event. We were then investigating the dependence of this kind of problem, or of the synchronization versus the key parameter of the system, namely the laser pump current, because it affects the dynamics of the system. Like I said, we have more intensity, and as a control parameter, it can also lead to transition between dynamical regimes. For example, between the low frequency fluctuations regime we had earlier and the coherence collapse regime. And this variation of this key parameter, how does this affect the synchronization? You can see that here. So here we have the normalized pump current, normalized versus the lasing threshold. And this is the maximum of the cross-correlation function. So for lower pump currents, we have very high synchronization or correlation values, and these decline with increasing pump current. And the question is now, why does that happen? Is that due to loss of the overall synchronization, so loss of transverse stability of the synchronization manifold itself, or due to this bubbling, to these intermittent desynchronization events? And for that, we have to be able to measure those. So how do we observe and analyze these bubbling events from time traces? Because this is basically experimentally what we can access. We can measure the intensities and then look at them. And for certain... Okay, now it's out. Thanks for the other one. Which doesn't work either.
Be connected.
The synchronization error, so the intensity difference is in some cases impractical because sometimes you have fast fluctuations, but very short ones, and that doesn't necessarily mean that there's a real desynchronization going on. So what we have been using, this, is the so-called sliding window cross-correlation. So this is basically the same thing as a cross-correlation, but only over a short window, in our case over 1 nanosecond windows, and these windows are shifted through the intensity time series, and so basically each point of the sliding window cross-correlation depicts the cross-correlation over this next following tau length window. And then we have a local measure of synchronization, and then because we have such a short window, we can account for very short events, maybe 1 nanosecond events. And this is how it looks. So this is now a time trace in the LFF regime, so low frequency fluctuations. You can see them here. You have these structures which are similar, and these are the most characteristic features are these power dropouts here, the intensity dropouts at the end of each of those cycles. This is a magnification of part of this time trace, and the time traces have been shifted upwards or downwards, so you can actually see what's happening. So we can see here that one of the lasers fulfills this dropout earlier than the other one, and here the second one follows, right? In the lower panels we have the sliding cross-correlation time traces. So value close to 1 would mean excellent synchronization, and the lower one, of course, bad one. And we can see that these dips in the synchronization or in the sliding cross-correlation correspond in time to these points of the power dropouts. And otherwise, after these power dropouts, as can be seen here by the magnification again, the correlation was actually really good. So it seems like we don't have a problem with overall transverse instability of the synchronization, but only these local features, these temporary intermittent times where we have desynchronization events. And what we can also see, exemplary by this thing here, is that the desynchronization is actually comparably long. In this case, actually, it corresponds exactly to the delay time. This event here, so in our case, that was like 75 nanoseconds. This is now the case in the coherence collapse. We can see here, this is actually a shorter time scale if you want to compare. These are 20 microseconds, and this is only 200 nanoseconds. And we see that the dynamics are have only the fast components. There's no slow component like in the LFF regime. And we can also see that these dips in the sliding cross-correlation happen quite frequent, much more often than in the low-frequency fluctuations regime. And again, these dips can very nicely distinguish the synchronized from the unsynchronized behavior as a local measure.
Konstantin, in these bubbling regimes, I mean, how far are you from the blowout bifurcation? I mean, you're close to the onset, or?
Actually, we made sure that it's far enough from the blowout bifurcation. So usually, I mean, even by the measure of synchronization errors, it's obvious that we have very well overall synchronization, only with these intermittent drops. So otherwise, we would see. I mean, if we were too close, then one would expect from time to time a certain breakdown of the synchronization over a longer time, right? Or not even synchronization at all. So we made sure that the setup was done such that we were far enough from this synchronization. And also, since Valentin did some simulations before and we transferred this to our experimental work, we could be pretty sure that we were far enough from the blowout bifurcations. So now if we want to characterize and quantify the bubbling, we need to define certain thresholds, of course, because we would have to say what we consider a desynchronized event. And unfortunately, these thresholds are, of course, arbitrary, but how else are we going to do it, right? So what we have here is again a time trace of the sliding cross correlation. And now we institute three different thresholds. First, the correlation threshold, C threshold, which says that the sliding cross correlation has to dip below that necessarily for us to consider desynchronized behavior. Then we have T threshold, so it's the duration of the event. So the event has to be at least as that long to be considered desynchronized behaviors or bubbling. And we have the separation or the inter-event interval threshold. So that means how far have these two dips, for example, to be apart for it to be considered two different events. Otherwise, if it's below this threshold, one would consider this one longer event. So these would get joined, basically. And with these three thresholds, we can now quantify, or can first distinguish these events, and then quantify them. So do statistics, basically, over the pump current as the key parameter we've been looking at. Okay. So these are now statistics in the coherence collapse regime. We have here the bubbling inter-event interval, so basically corresponding to the occurrence, so the frequency of these desynchronization events, and increasing pump current from up to down. And we can see with these logarithmic histograms, basically, that increasing the pump current means, on the average, shortening the distance between two successive bubbling events. It's quite obvious, right? So that means basically, the desynchronization events happen more often and more often, the higher the pump current is. And if we look at the duration of these events, we can see also more or less expected behavior. So we see that in general, the events, these bubbling events, get shorter. So the bubbling duration decreases as the pump current increases. Yes. Okay.
Is there some fingerprinting of the delay time?
I'm sorry?
Is there some delay time seen here? Or what is the magnitude of the delay time you use?
That's a good question. Actually, the delay time would be visible if we look at the corresponding plots for the low frequency fluctuations regime here in the duration statistics, because there would be a more or less solitary peak around this delay time. But since in the low frequency fluctuations regime we have very few desynchronization events, this kind of statistics wouldn't make sense, because it's just single events and that nothing much to show, right? But in general you're right. If we extended the scale to the delay time, which in our case was like I said, 75 nanoseconds, we would see more or less a single peak around this delay time, and that would correspond to these dips here, right? And for example, if we increase from this situation, increase the pump current only a bit, then more or less all of these dropouts would then be associated with the correlation dips, and then we have more events. Okay. Last part, an example for application of this kind of system and the synchronization of chaotic laser outputs is the key exchange protocol, namely, or basically, more specifically, the key exchange over a public channel. So, what we set up, or what this is, has been published by Claudio and Ingo and Vicente in 2007. And the principle is the following. First, we have two bidirectionally coupled lasers with a relay, like during most of the talk, right? And then the lasers, or the laser pump currents, are modulated with binary messages M1 and M2. These would be those two things. So either 0 or 1 with different legs. And this modulation of the pump current would then, of course, result in change dynamics, and it is also the messages can be more or less hidden in the chaotic carrier. And the important part is now that the lasers will desynchronize if they're sending different bits, right? Because they're in a different dynamical state, and if one laser sends a 1 and the other one a 0, then they have different dynamical states and desynchronize. But the beauty of it is that if they send the same bit, both the 1 and both the 2, both the 1 and both the 0, then they resynchronize, or they stay synchronized. And that would be that part here. This is basically just the difference of the two binary messages, and this is the corresponding intensity difference, including certain lags, which was present in the system. And we see the correspondence, right? And now this is used such that first the two people who want to communicate over this public channel or want to exchange their key just agree on a certain number of bits, synchronized bits that they want to use for a key, for some kind of cryptography. So let's just say they say, let's use the first 128 bits that are synchronized for our key, and if we have an eavesdropper in both directions, maybe, of course he or she can also access this kind of profile. So in these cases with the peaks, it would be obvious which bits were sent, right? But if the two communicators actually say we only use the synchronized bits, then the eavesdropper only sees this flat line, the 0. So he or she only knows that both have sent a 0 or 1, but can't say which. Only the two communicating parties can. And such, the eavesdropper cannot determine the bits, and then the key has been exchanged over a public channel with no cryptography necessary, and then this key, for example, can also afterwards be used for encrypted communications. But this is just one of many examples for which you can use synchronized calculators. So, to sum up, I tried to show you first via a generic approach, then with lasers, that certain symmetries and mismatches in such a bidirectionally delay-coupled system influence the dynamics or the stability of the synchronized state, the identical synchronized state in certain manners. For example, that the mismatch between the coupling and feedback strength changes the stability. So, for example, in our case, prolongs the intervals of desynchronization with increasing mismatch, but does not change or alter the dynamics in the synchronized state. A mismatch in the delay times changes the dynamics, but not in general the synchronization quality. And of course, if we have a delay mismatch, we have a identical time shifted synchronization, so not zero lag, but with a lag according to the mismatch. I showed you experimental results that we achieve very high correlation or high quality identical synchronization in a fiber optic setup using a fiber loop mirror as a relay, corresponding to the semi-transparent mirror from before. And I hope I could convince you that the main mechanism behind this loss of synchronization, for example, when increasing pump current, can be identified as bubbling, as they exhibit the intermittent desynchronization, so synchronization error, and that the increasing the pump current means an increase in the frequency of these desynchronization events. And also, I showed you one example for the chaos synchronization of two delay coupled lasers, and I hope you agree that those are or can be very valuable for the usage in different communication schemes. Thank you.
So now it's time for questions. And you know that students have some priority to ask questions. So, please.
Can you put the first question to show?
Very first time.
You're really writing with this, right? This would be that one.
Yeah. So there the coupling appears only linearly. Is this so because you have linear lines? You assume that you would expect that
x1 and time t minus tau and x2 and time t minus tau would appear inside F. It would be F of the field now.
No, F only describes the dynamics of the system as itself.
Yeah, so if you have feedback, the field comes back inside, so it should.
Yeah, sure. But this is just the problem that we had with the state variables, and I mean, since the system is coupled with the state variable itself again, then of course in turn via the delay goes into the F function, right?
Yeah. So then you have linearized because the student is small.
No.
It's linear propagation of outside relation. On the fiber, you have shown linear propagation. That's enough to produce the paper.
So then the F of x1 plus x1 times time tau. So, I mean,
Yeah,
the field here, the field acts on the carriers and everything. So the field now and the field that went out and came back. So it acts in the same way. I would no.
I mean, the propagated field after delay time tau then in turn changes or affects the present state, right?
Yes.
And then that in turn influences the carrier dynamics because the two equations are actually coupled.
Yeah.
But
and it does show in the same way as the field itself now. No?
okay, but the field now is basically, I mean, since this is like you said, this is linearly coupled, so the field now is then the sum of the present field, if you will, and the coupled in field. Yeah.
And then why is not F of x1 at t plus x1 t minus tau plus x2 at time t minus tau? That's what I expect.
Okay, but would this be really clear? I mean, this is a generic equation to show, right? I mean,
It's not linear because the coupling is.
I mean, if I show the multi-layer couplings inside these equations, then I don't know if it was.
This is just, I think this is just symbolic and it's not true. There are many equations there, and the coupling is only on the electric field.
Yeah.
And in usual electromagnetism, the field in a place, you can sum the different fields from different places.
Yeah,
and this is
you have to enter inside F.
Yeah,
they don't enter inside.
Why?
Why not?
It's just the
If the fiber is linear, they don't.
synchronization.
And just FYI, what is missing in this equation here, here, and here is the coupling matrix, which would then look like this, and this would then account for the coupling only affecting the field equations directly and not the carrier equations, like was criticized very correctly before.
So I have just the last one is what?
In the theoretical part, you have played with the coupling parameter mismatch and coupling and delay difference. And in the experimental part, only with the pump current. Have you tried to do the same thing in both places? Or?
We've tried to. And actually, I mean, at least the delay mismatch is, of course, in experimental systems present already, right? Because you won't be able, at least not in this kind of setup we've been using to achieve the zero delay mismatch. But to be honest, to achieve the high level synchronization meant tweaking the setup quite a bit, and we have not so far. We haven't done this systematic investigation of the delay mismatch in general. I mean, we are getting new experimental components, so different kinds of, for example, different lasers, which then would exclude certain other phenomena that occur in this kind of atomic system, and then it should be easily attainable to do this kind of investigation. I am very interested to do that, but so far, since there are other, I mean, these are mostly, for example, polarization phenomena, polarization-related phenomena, and these usually are detrimental to achieve the synchronization, and they are just disturbing everything. And then, since we can so far not really exclude this delay mismatch, and we have seen that the delay mismatch and the coupling mismatch makes the synchronization decrease very quickly, we would have, for example, to use our fiber splicer and equalize the delay length as much as we can, and then we can more easily do these kind of coupling mismatch investigations also experimentally, not only numerically.
Yeah, at some point of your talk, you tried to convince us that the bubbling is related to the dropout.
Mm-hmm.
However, if you look at the simulations, because in simulation you see it much better, when you have a dropout, what happens in one of the laser switches, so you lose any connection with the other one, that has nothing to do with the bubbling. The bubbling is related to the instability due to the fluctuation, due to noise that you see actually at much higher currents, because at much higher current you don't have any dropout, so the bubbling cannot be related to that one.
It's not related to the dropout exactly, but the thing is, this dynamical feature of this intensity dropout then in turn produces this desynchronization, because the basic principle also in the coherence collapse of this collision with an anti-mode and then the bigger or smaller ejection of this trajectory in phase space is basically the same principle. So we have in both cases, either with pump current small or big, we have collisions with transversely unstable antimodes, but it just turns out that in the FF regime, this then leads to the dynamical feature of the of these power dropouts, which is just not present in the coherence collapse. But the basic principle that analyzes those things is exactly the same. So, and as we were able to see as well, is that not all of those dropouts, which happen regularly. We have these cycles here. So with these cycles here, we always have this kind of dropout at the end of the LFF cycle. But we do not have always the bubbling event, which then would mean that in that case, the intrinsic noise in the system would not lead the two different trajectories of the lasers in phase space to later or earlier collision with an antimode, but as at the same time, right? So they both experience this power dropout, but at the same time, and that's why there's no bubbling or no desynchronization occurring. Which is actually very interesting, because in this case, we can, via synchronization, actually observe this kind of deterministic chaos, which this kind of chaotic trajectory down this mode ellipse, and these power drops is chaotic, but deterministic chaotic dynamic can be. And if we have desynchronization at these points, that would be bubbling, because we have noise-induced change in trajectory, basically, which then would mean an earlier onset of this power drop of this re-ejection in phase space, and then the other one follows after delay time tau, usually, but can also be short.
I have two quick questions. One of the figures you showed me reminds me one of the first talk I ever had that was by Claudio on the Sisyphus effect.
Yeah.
So it has something to do with this?
This is actually, this build-up process. Good that you mentioned it. This is actually just that. This kind of power build-up process here. So the trajectory going down here, and then suddenly we have this power dropout. So the intensity decreases suddenly, and the trajectory gets ejected here. This is actually just what is called.
In the case of Claudia, I don't remember anything about that, but it was also the delay was entering into the dynamics.
Yeah.
It was also the same thing.
Because I think the delay feedback case.
Okay.
The delay, in this case, the delay time influences the number of these modes. So if we have a very short delay, the jumps basically, in this case, frequency jumps of the laser system would just be bigger. If we have a smaller delay, and if we have a very big delay, those are very, very close to each other. So usually the frequency jumps are not just as big, but in general, the stability features here, like as shown here, are not influenced by the delay time.
Okay.
They're just the same.
And the second is, so you have motivated that delays everywhere, basically, right? And then you have shown a laser example, but if you go to the last your summary, basically the changes you describe are quantitative changes, right? Because you say it disappears, blah, 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 blah. So basically I understand that they are quantitative changes, not qualitative changes, right? So if this is true, if my understanding is correct, then my conclusion will be, okay, you don't care about delays, because the changes are quantitative, right? So I suppose that this message is synchro. So this is the question.
The thing is, without the delay, you wouldn't have the chaotic dynamics, right? So the point is that, okay, maybe I should have emphasized this a bit more, but the chaotic dynamics in the laser output, in the intensity output of the laser, is induced by the delay coupled feedback or the delay coupling. Without the delay, this wouldn't happen, but of course in reality or in nature, you don't have this. So that's
so in that case, you will expect you have more equations, you have chaotic dynamics already at the local dynamics, then you will expect changes, qualitative changes when you usually delay. So you have an equation. I mean, I'm trying to understand, I mean, if at the dynamics level is also very important the delay or not. I mean, what would be my expectation without?
Absolutely, yeah. Yeah.
That's it.
Okay, so I think that we can stop here, and thanks again.